Swayam Prabha. Digital India. Educated India.
Welcome to the class of high performance computing for scientists and engineers, and we are in our third module of this course, which is message passing interface or MPI programming, and this is 21st lecture of this course. This lecture is on communication using MPI. If we can remember, in our previous lectures we have discussed about the essential features of MPI which we require to know to start MPI programming, and we have also looked into a sample MPI program which is our first MPI program, LC Hello World program, that how multiple processors can be assigned in a distributed memory parallel computing paradigm to write Hello World on their own on the screen. So, we have looked into Hello World program in last class, and couple of things we have noted that for initializing a parallel environment, parallel synchronized environment across the processors, we need an MPI initialization command. This MPI init is a function for C program and it is a subroutine for Fortran program. So, all the MPI calls like MPI init comes as function in C program and comes as subroutines as in Fortran programs. However, we need to call a number of MPI functions to write an MPI program, and we have seen that there are 6 essential MPI calls by which we can parallelize any program, and there are also some more MPI calls by which we get more flexibility in writing parallel program, but these 6 functions are very important. And these 6 functions are MPI init, MPI finalize, MPI init initiates the MPI parallel environment across the processors, MPI finalize terminates that environment, MPI com size which tells us what is the size of the calculation, how many processors are involved, MPI com rank which tells us what is the rank of the particular processor in that MPI calculation, and MPI send, MPI receive. And another important thing we have also looked into is the communicator which clubs all the processors working in the environment, and this MPI communicator is by default called MPI com world. Virtually this is collection of all the processors which are connected through the network cable and executing the particular parallel MPI program together, and this is extremely important, and we will see in many cases when we try to communicate across the processors, when we try to synchronize certain things, we need to mention about this communicator, because this communicator and MPI com world, which is grouping of these processors which are working in the MPI mode, they will ensure that these processors are working together and any message being passed goes through the network which connects these processors. So, like if we think of a shared memory program, or if we think of a sequential program, we need to take care of the processors only, but here we need to take care of the fact that there is a network cable or there is a connectivity across these processors, and we need to do certain things across the using that network cable or the connectivity. I think the better way to mention it as connectivity, because we are looking into software right now. And now message passing interface or MPI is developed to facilitate certain work which is obvious from its name, which is message passing. So, within that communicator is a group of the processors working together in the distributed memory algorithm, combining their the connectivity or interconnect between them. So, within that communicator, if we have to transfer certain message, we need to use some of the protocols, and these protocols are obviously new because this I mean, if we have background on sequential programming or shared memory programming, these protocols are very new to us, because this is first time when you are asking one processor to communicate with another processor. These things we have not seen till now in our parallel computing discussions. So we will focus on this type of these communications right now. So this particular lecture, as I said, is communication using MPI, and we will look on the key aspects, which are point to point communication, and one is point to point communication. We can see, point to point communication and collective communication. These are two modes or two models of communication in MPI, and we will look on protocols for point to point communication, array handling in point to point communication. Point to point communication, we will discuss it, but basically means when one processor is communicating with another processor, and we will see that how it can send large arrays from one processor to other processor, how these communications are done, and which of these what is a blocking and non-blocking modes of communication in this. And then we will see something called collective communication, when one processor is communicating with all the processors in the group, or in the communicator group there are multiple processors. When you club them, combining the interconnectivity, we call it a communicator. So within the communicator, if one processor tries to send something to all to the entire communicator, all the processors present there, this is through a collective communication. We will look into collective communication, and we will look into MPI reduction function. In OpenMP we have looked into reduction function. Reduction functions are very important in scientific computing. We have discussed that if there is one if there is some calculation which has to be done parallelly by multiple processors, and each processor comes up with their local value, and finally all these local values are to be combined to get a global value, reduction is the right operation for that. We have seen in OpenMP reduction is a very optimized communication. We will also see for MPI there are similar reduction functions, but now these reductions are not in shared memory. These reductions are happening across distributed memory. That means different computers are sending data to one computer who is collecting all and processing the global information out of that. We will see about reduction functions here. Well, so as the processors have their own separate memory space, any communication between the processor is ensured by data transfer among them. This is the basic fundamental concept of communication in distributed memory processing, that as there are multiple processors and each processor has its own memory space, so they cannot share any data in between them through the memory connectivity. The memories are disjoint, and I mean, memories cannot communicate with each other. Memories are in the motherboard, which memory cannot send any instruction, memory cannot do anything, only the processor can access memory and process some data. So if there is a requirement that one processor's data space or address space has certain elements which is required by another processor, this has to be communicated in between the processors. So it is like that. Again we come back to our money sharing example, that I have something in my money bag. I have 100 rupees note in my money bag, and somebody needs that money. I mean, I am okay if I can give that money to him, but the money cannot go directly from my pocket to his pocket. I have to take the money and send it to him. Similarly, information cannot directly go from one memory to another memory, because these are the disjoint memory spaces. The processor has to identify that piece of information and do a data transfer across the network cable or across the interconnect switch, and send that data to the processor who wants that particular information. So any communication in a distributed memory system can only be achieved through a data transfer process. Now these data transfer models, there are two models of data transfer. One is point to point communication, which can be blocking or non-blocking, synchronous or asynchronous. What is point to point communication? That if we see that these are disjoint memory spaces attached to different processors. So, this is an array, these are array locations of memory in the different processors. And now I1 to I2 minus 1, this part of the memory is attached to, I mean all these the elements present here are attached to some other processor 1 say. And so, let me write the processor numbers here, that processor 0 is attached to this memory space, processor 1 is attached to this memory space, and processor 2 is attached to this memory space. So, now processor 0 needs this information which is given to processor 1. This information is required by processor 0. So, it has to get this data, or it has to do a data transfer from processor 1. Similarly, this information, so this is required by processor 2. So, it also needs to take this information from the I mean processor 2 needs to get this information from processor 1. So, one processor 0 needs to talk to processor 2, what happened, and processor 2 needs to talk to processor 1. If they have to get some, I mean processor 1 needs some data from processor 0 needs some data from processor 1's memory space, processor 2 also needs some data from processor 1's memory space. They have to distinctly talk to processor 1 and ask for this data. So, in a network system, one point is one processor. We can think like the processors are connected through a network and one of the points are one of the processors. So, one point needs to send data to another point and it has to receive it, and there is another point which needs data from that the other point. And so, it is a point to point communication. That means, one point will take data from the other. When processor 0 takes data from processor 1, processor 2 does not know about that this is in between these processors. Similarly, when processor 2 takes data from processor 1, processor 0 does not know about that, this is in between the other processors. So, this is which is very individual data transfer among two individual processors, and we call them point to point communication. The other one is collective communication, which is one to many, many to one, or many to many, and this also includes reduction. What is that? That one processor will send data to all other processors, or each processor has some amount of data and one will collect data from all of them, or each processor has some amount of data, this data will be combined and will be given to all the processors. So, this is not a transfer across two individual processors. It is, this transfer is visible to all the processors and each processor gets effect of this data transfer. So, this is called a collective communication. First one, you can say that like I want to give somebody money, so nobody else will know that I will do a account transfer and money will go from my account to his account, fine. And the next one is that is point to point communication, and when our government announces some plan and everybody gets some money, Jan Dhan account, everybody is getting money in his account who are member of that. So, it is a collective communication that from government's account, in everybody's account money is coming. So, it is not a point to point communication, and also everybody is aware of the fact that this policy is there, therefore, all are getting money. So, when collective communication happens, address space of all the processors are aware of that this particular information is being broadcasted to all other processors from one particular processor, or one processor is gathering data from this particular processor. There are few examples like broadcast when data is from one processor is given to all the processors, scatter when there is data in one processor and part of it goes to all other processors, or gather when different data is there in different processors and everything is comes and combinedly received by one processor. And this can be done by single processor or it can be done by many processors. At the same time, multiple processors can get copy of this combined data. And there can be reduction when each processor has its own local value as we can see, for processor 0 has 1, processor 1 has 3, processor 2 has 5, processor 4 has 7, and then everything is combined, summed up, and processor 0 gets this combination of summation of that, which is 16. So, it is like a reduction operation. This is also a collective communication. So, we will first focus on point to point communication, and point to point communication means one processor is sending data from its local address space, because the local address space is the only memory which is visible to the processor. So, one processor is sending data from its local address space to another processor. How can it send data? It will pass some information, it will identify a location in its local address space, pass that data through network cable, the other processor will get a copy of this data. So, it is like taking a data and copying it to somewhere else. Like if you are using a file transfer protocol, you copy a file and put it in another computer's memory. It is like that. So, you have some data, a copy of that will be taken through the interconnect network and will go to others processors local memory space. So, this data will be sent as a packet of data. It is not like any amorphous grains of data randomly sent between them. It is a packet of data. So, one processor will identify a data that these are the components of that data which has to be sent, some elements of array or something like that, and this will go to the next processor. And this, when it is sending it, few things are important. Who is sending it? Well, he must know that to whom it will be sent. Okay, I want to transfer money to someone's account, I know the account number, otherwise I cannot transfer the money. Similarly, the processor who is sending the data, he must mention that this data will go to him. Now, he has to also tell that what is the data type, what is the size, he has to tag the message. Similarly, the processor who is receiving the data must know that this data is coming to him and he must be ready for receiving the data, because sending is an operations which the processor is performing. Similarly, receiving is another operation which the other processor or the remote processor will perform. So, it is not that one processor will send the data and that will surely be received by the other processor. The other processor also have to be able to perform the job of receiving. That means, he will know who is sending the data, he will receive the data from him only, what is the data type, data size that should match. I mean, I am trying to send an array and some other processor is trying to receive an integer, there is a data type mismatch, and I am trying to send a float and other is trying to receive an integer, that will not happen. Or one is trying to send an array, another is trying to receive a scalar, that will also not happen. There should be matching of the data type and the size of the data, and the tags should match. If I will discuss why tag is important, but there is a matching tag in the data, and a send is incomplete unless this is received. Well, why is it so? If a processor sends the data to another processor, the other processor has to receive it. Now, you get back to the idea of bank transfer, account transfer of money. You transfer money to somebody's account, however, there is an error and the money is not sent. So, the money will get back to your account, money will not be deducted, it will come back to your account, and you have to do certain things. Your account will, who is processing your account, he has to do the process that the send is incomplete, so it return back to this account. Similarly, one computer who is sending data to others processor, if the data is not received, I mean, then the operation is not finished. Then you do not know, the processor must be aware of that it has been finished. If it is not been received, then there will be a stalemate in the processor. It initiated some job which has not been finished, so it cannot do anything else probably, or even if it does something, that there is an issue there. So, a sending of data will always be complete unless it is received. We can think of another example, like I mean, you are going in a bus and you give rupee note to the bus conductor, he will give you back the ticket. So, but if you give him the note and he is not giving you back the ticket, or he is not receiving the note, you are stalled, you cannot do anything else, you have to get the ticket. Or the reverse, he is giving you the ticket, but you cannot collect the ticket, he cannot go to the next passenger. So, simply sending an information is not sufficient. Any send has to be complemented by a matching receive. This is extremely important when we will look into details, that any processor who is sending the data, there has to be a matching receive of the data, we will see that, and the sent message must match the received message. Otherwise, I mean, you are giving the bus conductor 50 rupees note, and he expects something else, he expects a credit card, he is going with the punching machine. This is not going to happen, he cannot punch the note. So, what you are sending and what the receiver is expecting, this should match. Well, now what receiver expects? It is the programmer's job, we mentioned earlier, to mention what will be sent and what will be received. So, programmer has to make it sure that the sending message and receiving message must match in terms of the data type, in terms of the size of the data, in terms of the source and destination, also in terms of the tag, that this is written on top of that envelope, that this data has some certain header or some message, and the receiver should know that this is that particular data which is what he is trying to receive. Well, so every message document therefore must have two components, the message which is being passed. One is a sending instruction, a protocol through which one processor will send it, there is certain syntax for that. Another is a receiving protocol, a protocol through which the receiver will take the message and put it somewhere in its local memory. So, there has to be a similarly another syntax for receiving the message. The sender send, there should be a destination address to whom it is being sent, it is like a business address. What can be an address in an MPI parallel system? It obviously it will be rank of the processor, that when a processor is sending data to this particular processor, it will be, the processor will be identified by its rank, and destination address means rank of the receiving processor. A message location, which data will be sent. So, the processor who is sending it, in his memory, what is the location of this data? What is the address of the first element of that array which will be sent? What is the pointer to that? A message data type, which type of data is being sent? A message size, how big is it in that particular data type unit, and a tag. And the receiver will have sender's address, who is sending it, receiving processor should know from which rank this message has been sent. What is the receiving location? Once the message comes, where should he keep it? So, the sending location is in the sender's message location is in the sender's end, is in the sender's local memory. This is in the sender's local memory, and this is the receiver's local memory. So, we can write this is sender's memory, and this will be in the receiver's memory. So, a space in the receiver's memory in which this data will be accepted. It also requires a compatible data type and size combo, that this particular data of this size has been sent. When the processor who is receiving it, he also should give a compatible data type, that if he is sending an integer, he should be ready to receive the integer, and also the size should match. I mean, we know all these things, the integer, float, double precision, character, all has certain space in terms of byte, in terms of bit. So, in case this data type and size combo matches with the sending, though the data type may not match, but what this is sending few bytes of information. So, in case the receiving bytes match, the data transfer will be successful, but the data type real to real, integer to integer, float to float, that also has to be matched for right nature of the data being accepted. However, we will see some example, but the data type and size combo must match in order to fit, in order to see that this data has been sent and I can receive the entire data. So, the receiving location will be mentioned, and there should be enough space in the receiving location where it will be received, that has to also be mentioned. A matching tag, this data comes with a tag from sender set. The receiver end also should have a matching tag. In a program, especially in a program with high complexity, there can be multiple sending and receiving between two processors. Processor 1 is sending data very often and processor 2 is receiving that data very often. So, when one particular data is coming from a location in the sender's end, that data will be received in a particular location in the receiver's end, and that is required by the program. You need to know that this data is coming from sender's end and this data will be received from at this particular location. But if there are multiple send and receive, there are multiple data coming from the sender's end. Now, each of these data has to be received and located in the designated place by the receiver. Therefore, how will it know that which data, the data which is being sent by the processor, where it should go? That will be identified by the tags. If there are multiple sending of data, multiple instances data is being sent and the receiver is receiving it, through the tag it will identify that this data is meant for this particular location. So, a matching tag is required, like you are getting mails from same sender, but you identify that these mails are for this particular purpose. Your boss is has sent you 3 emails, and one email is regarding a publication, another email is regarding some information regarding your last week's work, the third email is regarding some file in your cabinet which he wants readily. So, all these 3 emails have 3 different utility, and you identify which email has to be replied in which manner and what are the relevant job corresponding to that email by the email header. Similarly, this tag is like email header, through which the receiver will identify that this data is for this particular location. Well, and the status, which will identify the correctness of the data transfer. If the data transfer is right, you will see some certain things, some certain values in the status message. If the data transfer is wrong, you will see garbages. We will look into the status later. And what is further important here are the data types for message passing. We know, we are aware of this data type in Fortran: integer, real. In C it is float, double precision, complex, logical, character. These are the data type we use for computing in simple sequential computing environment. We use this data type. Now, when we are doing message passing interface, we are using message passing interface or MPI, we are doing distributed computing, and we are using an architecture which is developed by bringing multiple computers together, and this can be very heterogeneous. There can be computers with different operating system, or different versions of operating systems, different versions of some other softwares, and they are connected together. And the meaning of data packet, meaning of integer, can vary across the processors. The size associated with the data, how they are stored, how they are accessed. Also, this data is being sent through a communicator, which is not a simple computer. Therefore, when we are considering about a data in a MPI data transfer, this is a data which is in transit, which is being transferred across the processors, and once a processor receives this data, it must know that it should map to the particular data type the processor is or the compiler processor or the OS or the compiler is using for its own work. So, the data in transit through the communicator is in nature little different than the data the processor the compiler considers while working through the program. And therefore, when we are using MPI, a derived data type is used, that these are MPI derived data. This data is for data transfer across MPI, and for each of the data type in your Fortran or C++ program, there is a matching MPI derived data type. When data transfer takes place, we need to look into the matching data type, that the data, while doing data transfer, we will not say that integer data will be transferred, we will say that the MPI derived form of integer, which is MPI integer, will be transferred. Why? Because this is not like a simple data type which is being addressed by the OS of the computer and the compiler. This is a data which is this data is a packet of information which is being transferred through MPI protocols. So, there might be heterogeneous systems which are connected through the interconnect, and MPI has built a communicator across them. So, the data in transit must follow MPI's own data type, and therefore, we use MPI integer, MPI real, MPI double precision, or in case of C we will use MPI float, we corresponding to the Fortran data C data type. So, when this data type will be transferred, we will use the MPI derived data type, we will not write simple C or Fortran data type here. And message communication protocols are very specific to the data types. If you see right that I am transferring a MPI double precision, it will assign bits as per a double precision number which will be in transit through the interconnect network using MPI protocol. It will be different obviously than a integer variable which is in transit. So, this is very important that while doing the data transfer, we must mention about the MPI data type, not the simple data type coming from Fortran or C compiler. And the send and receive protocols are important now. So, we know that when sending a data, we need to find out which data is being sent, what is the size of data, what is the data type, and what is the MPI data type. We cannot write integer data is being sent, we have to write if the variable is integer, when that will be sent, it will be during movement, it will be considered as MPI integer. And what is the destination, the tag, and the communicator, that is usually MPI com world, that is the communicator. So, the input parameters will be the buffer, which is the initial address of the sent, the count, number of elements that will be sent, the data type, MPI derived data type matching with the buffer data. Buffer data is the data which has been taken from the address space of the sending processor and to be sent to the receiving processor. Now, what is the data type of that buffer data? The data in the buffer which will be sent to the through MPI, and there should be a matching data type. If it is integer, the MPI data type will be MPI integer. If it is float, MPI data type will be MPI float. If it is a double precision data, MPI will be MPI double precision, so on. The destination or the rank of the destination processor, the message tag, and the communicator, which is by default MPI com world. If you are using default communicator, mostly we will use that. And the receiving protocol will be MPI receive void star buff. Now, this is where the data will be stored, we will see that MPI int count, MPI data type, int source, tag, MPI com, and status. This is the protocol. When you write the function, the function will give you an integer value, but you have to call this function for doing data transfer. The output of doing a receive protocol is buffer, that is the receive buffer. From the send the buffer data, there is some buffer through which data has been taken by MPI, and if MPI send is there, the processor has sent this data to the receiving processor. As the receiving processor receives it, it puts it in a buffer which is in the local memory of the receiving processor now, and there is the output. So, as the data transfer takes place, you get some data in its buffer. Well, the another output is status. If it is successful, the status is success, and we call it MPI success. It is a different type of variable. It is a structure variable, and the output is MPI success. So, if it is true, then if the data transfer process has been successful, then the status will be in some MPI success. So, these are the outputs. The data received, that is the output of receive call, and the status successful or not. And the input parameters are that while writing this protocol, you have to mention the count, what is the number of elements that is in the send buffer. The same number of elements should come in the receive buffer. The data type, source from where it is coming, tag, and the communicator. Well, now this is called a blocking send and blocking receive. That means, as the processor has sent the data, it cannot do anything else till the send is being finished. Similarly, other processor which is receiving the data, as it has started to receive the data, it cannot do anything else till the receipt is done. The processors will be, the processor's jobs will be blocked, execution will be blocked at this stage, and in this particular case a send has to be matched by a receive, because send is not finished unless received is matching received is receive command in the destination processor has been executed. Similarly, destination processor receiving is not finished unless the source processor has sent the data. So, there has to be a matching in between them, otherwise there will be a bottleneck. We will see about these things in next few lectures. Thank you.